Well, welcome back, guys. I see the audience is getting smaller as we progress toward the end of the semester. That's okay. Anyway, just a reminder on a few points is don't forget Tuesdays. Tuesdays will be set up for excuse me. Oh, I got one more here. Tuesday set up to do a study day, so I'll be here. Come in with questions. Uh, the plan today is to finish up chapter 14, which won't take us the full time. And then from Tuesday, we'll do the study day. And then next Thursday, we'll start chapter 15, which is the last one. That also is a short chapter. So you will probably get it knocked out next week. And if we don't, whatever slides we got left, we'll do the following week, and then we'll open that up also to be another study day. So good opportunity for you to go back stuff. If you have any questions, bring them in here and we'll go over them. Okay, now also remember that all the assignments, with the exception of the exams, those are a one-shot deal, are still open, but there will be a penalty charge on there. Now, I debated this and I come to the conclusion I'm going to give those of you who have missed previous assignments to make them up. I'll send an email to that effect about being able to go back and do them, and then I'll take off the penalty. But you have to do them by a certain time. After that, you have to receive the penalty. A reminder, the homeworks, the lowest two are dropped, okay? And there are two attempts per homework, if you didn't know that, but hopefully you do. And Canvas will keep the highest score. Now, sometimes some people have done the homeworks early chapters, and we're happy with that grade, and then do the second attempt. You can go back and do the second attempt, but Canvas, thinking it's a late attempt, will give you the penalty. If you go do the second attempt for a previous one, you like that score better, let me know, and obviously I will take off the penalty for that, for your second attempt. So, okay, any questions about that? All right, so let us jump on to chapter 14. The other aspect, you're free to come to my 1 o'clock class. And on my Friday class, which is at SEC, you're also free to come to that. That is from 1 to 3:40. They also are on chapter 14, the ones in SEC. So even though you signed up for a particular time, you're more than welcome to come and, do the other sections if you have questions. So feel free. Same link, same everything. Okay, chapter 14. We ended up on this slide here. Now, a refresher. We've been talking about IMF. Those are intermolecular forces. These are the forces that occur between molecules as compared to intramolecular forces. And those are basically the type of bond, okay? So our deal in here is intermolecular forces, interactions of molecules with each other, and what effect they have on properties. Specifically, I'll be talking about these 4 properties. One is vapor pressure, boiling point, surface tension, and then viscosity. Now, we're going to discuss those here in a little more detail. But just to rehash, when we're talking about intermolecular forces, we can have a molecule. Let me draw it this way. Let's say we have a molecule, and it's going to be a sphere, whatever it is, okay? And there's an interaction occurring, and I make that by a dotted line. There's an interaction occurring between these two molecules. Now, generally what happens is here that we end up with a dipole in each molecule. And so the partial positive will line up with the partial negative of the other molecule. Keeping in mind we're 3-dimension here, so I'm just showing you 2-dimension. And so these forces right here, this interaction here, has a big factor on on some of the physical properties such as vapor pressure, boiling point, surface tension, and viscosity. Now, we have 3 forces to refresh your memory. The strongest of the force, the most strongest, is basically the hydrogen bridging force. Okay, now that, and then the next in strength would be number 2 would be dipole force. Okay, and then the weakest force will be the London dispersion forces. Now, the London dispersion forces, once we had defined that molecule, that the molecule as being a nonpolar molecule, then automatically the only force involved with that is a London dispersion forces, okay, which is the weakest. Now, if the other molecules require that you have a dipole, okay, a dipole. And so we have dipole force, which requires a dipole, like the example I gave down here with the two molecules interacting with each other. And then we have what's called the hydrogen bridging force. Now, that is like a dipole, but it's a little more special than just a dipole. That only occurs for a hydrogen bonded to nitrogen or oxygen or fluorine. Okay, only when you have that scenario. Okay, even though that is a dipole, but that's a special force of a special strength, a higher strength, we call that hydrogen bridging force. If it's not a hydrogen bonded to nitrogen, oxygen, or fluoride, the only thing you got left is just a dipole, straight ordinary dipole force. So we have to determine whether a molecule, what type of polarity it is, and then from there determine what force it is, 1, 2, and 3. Yes, there is the 4th force, which was called the ion dipole. Now, remember this, ion, which infers we have an ionic compound. Okay, metal-nonmetal combination. And most of the time having an ionic compound, the dipole part is the aqueous system or being water. And so if there is no ion or ionic compound mentioned in the question, any of the sort, then we're dealing with just simply 1, 2, and 3, which are simply covalent compounds. Okay. All right. Now, with respect to vapor pressure, we're all familiar with a soda. I don't have I wish I had a bottle here, but let's say we got a bottle here of your favorite soda pop. Okay. All right. Remember, I'm not an artist here. And I got a liquid here, and you got your soda pop in here. And I'm going to draw the molecules in there as just straight ordinary spheres. Now, that empty area from here to here, that's just, we call that a headspace, just air, right? From a regular soda pop container. And it's capped. Okay. Now, there are molecules in the vapor phase. Okay. Don't believe me? Take your soda pop, uncap it. What do you hear? You hear the carbon dioxide coming out. Right? And so if we were to put a pressure meter up in there, it would look something like this, maybe on the side with the needle that measures pressure. We can actually measure that pressure in the air, in the headspace here, just like we measure pressure in your tire. Okay. We call that vapor pressure. And the reason it's called vapor pressure is because these molecules, some of these molecules are going into the vapor phase. And obviously, the more, keep in mind, the more molecules that go into the vapor phase, the higher the pressure. You know, just like you put air in your tire, you're pulling more molecules of air into your tire. Guess what? Pressure goes up. Okay. Now, if you take a soda pop bottle and you shake it, pressure builds up, correct? If you open that up, that whole thing might just squirt out. But if you keep it capped, and you know, you're taking a soda pop and you dropped it and it pressure builds up. But if you leave it, what happens? Some of these molecules that are in the liquid phase get pushed up into the vapor phase, and the pressure goes up. The vapor pressure goes up. Now, as we sit there, as you let that bottle sit there, it's going to go back to equilibrium. Remember equilibrium states where the arrow can go in both directions. So some of the gas molecules will go back into the liquid until such time that we're back to equilibrium. The pressure goes down. You can open that container without risking filling everything out. Okay. Now, when we talk about intermolecular forces, I want you to think about the interactions, and I'm going to use these in a different color, that occur between these molecules. Okay, and I just got these intramolecular forces. Now, think about this. If these forces are pretty intense and they're strong, these molecules get attracted to each other and are held together very strongly. Well, that's going to have an effect on how many of these molecules go up into the gas phase. And so if those red forces, I made them red here, are strong, there's going to be less gas molecules going into the gas phase. If they're weak, okay, with respect to those three, if they're weak, then more gas molecules go into the gas phase and the pressure goes up, which means the vapor pressure goes up. Okay, so that's what we're talking about. We're going to be talking about the vapor pressure and how these interactions affect whether that vapor pressure is greater or less, relatively speaking, when we compare two different compounds. We're not going to be able to tell you specific, exact magnitude, but we can say between A and B, which one is going to have a higher vapor pressure based on their polarity. And then that tells us what type of force they're dealing with, okay? But keep in mind, these forces as how these molecules are held together relative to each other. The same is true for boiling point. Again, boiling point is a measure of the temperature that a liquid goes into the gas phase at 1 atmosphere. Okay, so water, for example, boils at 100 degrees Celsius, 1 atmosphere. So in 1 atmosphere, as you heat up some water and check its boiling point, it boils at 100 degrees. Again, if these forces I got written in red are very strong, okay, it's going to take a lot of energy to break those forces up. So the temperature goes up because it's taking more energy to break it up. So I got to heat it a little bit longer with more energy to break those forces, to drive those forces into the gas phase. Okay, and the converse is true. If those forces are relatively weak, then it won't take much energy to get those things to evaporate. You're familiar with, obviously, boiling point of water. Next time you put a pot of water to boil and make some spaghetti and it starts to boil, and guess what? It's boiling at 100 degrees Celsius. You may have some acetone around you, which is a fingernail polish remover. You know, you remove it, it's very volatile. It evaporates very readily, okay? Because those forces in the it's called acetone, the fingernail polish remover. The forces in the acetone molecules are relatively weak, so they separate relatively at a lower temperature than compared to water. Surface tension, again, it's a matter of how the liquid beads up on the surface. You're familiar with this probably. Next time you wash your car and you get it waxed up, and if you get water in it, the water beads up, right? That is surface tension. If a molecule has very high IMF interactions or high energy interactions, then it would beat up more than the liquid that has weaker IMF interactions, and that the weaker one would more flatten out. They would have bead, but actually flatten out. And then viscosity is a measure of the resistance of flow. If molecules again have strong IMF interactions, those molecules are holding on to each other much tighter than relative to something else. They're going to flow much not as readily. Honey versus water. Okay, we know that honey flows very slowly. Those interactions are pretty strong relative to water. And so the viscosity is greater for honey than it is for water. Okay. All right, so let me clear this up. So we just talked about vapor pressure, and that's the forces that molecules interact with each other. Okay. And notice we've been talking about having to put energy to break up the interactions, but you know, some of these things, some of these interactions, you don't need energy. Hey, think about it. All right, I get a glass of water and I put it on the kitchen tabletop and I leave it there for a week. Obviously, when you come back, what happens? It's evaporated, right? Well, you might think, well, wait a minute. I didn't heat it. Why did it evaporate, right? Because you should come back and you should still have the same amount of water, but we all know that's not the case. We know when you have an open container of water sitting out there, with time, it will evaporate. How on earth does it evaporate? Well, if we give it some thought here, you can see if we have let's say a cup and you have liquid, some liquid, we call it water. And again, and it's the open container. So we got these water molecules here. I'm over exaggerating it, but let's say we got them here. Well, these water molecules are moving. Unlike a solid ice where the water molecules are frozen in position, the water molecules relative to each other move. They have kinetic energy and they're bouncing up against each other. And these guys that are on the surface, well, one of them could bump up against the other and transfer that energy, the one that's moving, onto the one that's on the surface. And that can be enough energy to cause it to go into the atmosphere. And that's what's happened. That's one way to demonstrate that molecules move. They are moving in the liquid phase. So eventually these molecules relative, the concentration drops, and with time, it starts to evaporate. You're down here at the bottom where the container is literally almost open after a few days. And that's just simply because the molecules are moving around and they're picking up enough energy, or one molecule kicking the other one into the atmosphere without having to put any heat to it. But obviously, it's going to be a closed container, open container. What am I saying? In a closed container, you get it to equilibrate and the liquid won't evaporate. Okay. Obviously, no lid, they float away and they're off in the atmosphere. You know, the same is true for gases in your container. Soda pop, you leave it open, uncovered for a couple of days, come back, and guess what? It's nice and flat. Okay, because all those gas molecules in the open container eventually went out and evaporated. Now, if we have a lid in the container, like I explained, we have a pressure buildup. Okay, pressure, and that is what we call the vapor pressure. Okay. Now, think about this question here before you answer it. Vapor pressure is the pressure exerted by the gas molecules above a liquid in a closed container. Okay. And so obviously, like in the scenario where you put more air into your tire, the pressure goes up. Okay. So now they're asking you here, a stronger IMF, would that produce a higher or a lower vapor pressure? A stronger IMF. Would my vapor pressure go up or go down? What do you guys think? What we got? It would be higher. Okay. Well, let's think about that for a moment. Okay. Lower. Okay. We got lower and higher. So we got a 50-50 chance here to be correct. Now give it some thought. You have a container. Okay. We got another one. We got it. Okay, we got how many lowers? We got two lowers, we got one higher, lower, and two highs. All right. So we're kind of split here. All right, let's do this. We got a closed container and we got a liquid in here. Okay. And again, I'm going to draw spheres to represent. Okay, lower because less likely to break away. Okay. Exactly. Okay, but why is that? Which is correct. Okay, so let me have you look at it this way. We got a closed container, so we know the molecules won't go away. And we got these in solution. The circles represent the molecules of whatever we're looking. And we have a few in the air. So we could measure the pressure with a gauge here. We have a gauge here that measures the vapor pressure. Okay, these are just gas. Same type of pressure gauge. We can measure your pressure in your air time. Now, if the IMF interactions, which I'm drawing with a yellow here, they're not bonds, they're just interactions. Remember, they're just forces. If these forces are very strong, then the likelihood of the liquid, because this is in the gas phase up here, and this is in the liquid phase. If these forces are strong relative to the three forces, let's think about the three forces, keep that in your head. The stronger of those three forces are going to hold these molecules tighter to each other. Okay. And therefore, less likely molecules being injected or thrown up into the vapor phase. Okay. Because they're being held down tighter. Now, if the forces are weak, like London forces, then these forces are not going to hold on to each other as well. So there's going to be a lot more molecules in the vapor phase. Okay, see how that works? Now, keep that in mind. It's a matter of how they interact with each other in the liquid phase. If they interact strongly, it's going to affect the properties. In the vapor phase here, in the vapor pressure, it interacts it such that the vapor pressure is lower, okay? Because they're less likely to break away because they're being held tightly with each other. Let me clear my beaker here. And so if we look at this diagram, okay, approximately the same amount of liquid, assuming it's a closed container, the question is, which has the weaker IMF? Well, the weaker IMF will be that interaction in the liquid phase. And so A, based on this diagram, seems to be the one with the weaker IMF. Why? Because there's more gas molecules in that diagram than A. And because there's more gas molecules in the gas phase, guess what happens to the pressure? It goes up. Okay. And so the weaker IMF interaction, the higher the vapor pressure, because there's less of these molecules doesn't take much energy to get these molecules to break that interaction up between the molecules, okay, and drive them into the gas phase. Whereas you can see over here in the B, we only have, a small amount of gas. This is the gas molecules. And so that that infers that that interaction between the molecules is much greater than in B than there is in A. You see how that works with respect to these properties and with respect to the IMF interactions? Okay, boiling point, analogous. Okay, this time we're looking at the pressure at the boiling point. If our IMF is stronger, then our boiling point will be higher for the same reasoning because the molecules are being held closer together, tighter, I should say. And so B, for example, just the vapor phase being higher, or lower, I should say, means that to get this B to boil, I'm going to have to put more energy into B to get the molecules into the gas phase than I would have to for A. And this is a good example for if we were going to do compare and contrast, because this would be a good example of, let's say, this could be water versus ethyl alcohol. Okay, they have very similar polarity, but the forces involved are a little bit different. And so ethanol would boil. Whoa, I got that reversed. Hold on. Let me reverse that. I got ahead of myself. If I wanted to compare, no, I was right, ethyl alcohol, because the interactions for ethyl alcohol are much less or weaker. It would boil at about 78 degrees, and water over here will boil at 100 degrees Celsius. Okay. Again, due to the interaction of the molecules in the gas phase. Boiling point, stronger IMF, higher boiling point, as I stated. Okay, which is also true with what we call the melting point. And that, boiling point is that point where the liquid is changing phase to the gas phase. And melting point is that where the solid is changing phase to the liquid. That is a melting point. And so, for example, ice melts at 0 degrees Celsius and it boils at 100. Okay. All right. So you can also say, if they ask you, say the boiling point, they may refer to who's got the lower melting point. But the same reasoning we just went through with boiling point will be true for melting point. Surface tension, again, that's a measure of how these molecules are held on to each other. So a stronger IMF would have a higher surface tension. Okay. And an example would be here between A and B. You can see that A beads up a little great more so than B, where B kind of flattens out. This would suggest that A has a higher IMF interaction than B does. Okay. All right. And viscosity, same reasoning again. Oil flows slowly, it's high viscosity. Vodka, for alcohol, flows rapidly because low viscosity. Okay. And so again, a stronger IMF results in a higher viscosity for the same reasoning, because the molecules are being attracted to each other and held strongly together than a lower IMF. Okay. Well, let's do a compare and contrast. We can't actually give you absolute values and say, okay, we can say this chemical has a boiling point of whatever. All we can do with IMF is to do a relative comparison. Okay, we can compare. So first thing we got to do, you might be given an example here. They'll say, let's compare ammonia and fluorine. first thing we got to do is determine what IMF they have. Well, to determine that, we first need to determine what type of polarity. Obviously, there's no ion dipole here because we're talking about fluorine and ammonia. There's no mention here of ionic compounds. Okay, so if you haven't done so yet, you might as well just memorize the structure for ammonia because we've done this a number of times. This is the Lewis dot structure. Okay, and to figure out the polarity of the molecule, sometimes you need to draw and determine the Lewis dot structure for it. So you can make a more educated guess as to whether it's polar or non-polar. Ammonia has a group, it has a lone pair on the central atom. Okay. I mentioned way back when that once that occurs, once you get a lone pair in the central atom, without question, you have a polar molecule. Okay. Now, once we determine that, we got to figure out what force are we talking about for ammonia. Okay. We know it's polar. Okay. So it's being polar eliminates the London forces. And I was going to go through hydrogen bridging. That's correct. And let me go through the stepwise until you're comfortable with it. But obviously, since the fact that it's polar, we can eliminate London dispersion forces. That's out of the way. We can eliminate ion dipole, right? Because there's no mention of ion dipole. So the only thing left is a dipole and hydrogen bridging force, right? Well, yes, we got a dipole here. Nitrogen hydrogen bond, it's a dipole. But guess what? We got nitrogen bonded to hydrogen. So the force here, it's not a dipole, but it's hydrogen bridging force. Okay. All right. Then we look at fluorine. Now, notice when we talk about, they say fluorine, remember fluorine, chlorine, bromine, etc. Always diatomic. Always diatomic. So that's F2. All right. Now we look to determine the polarity. F2, two fluorines bonded together of equal electronegativity. We have a non-polar species here. And that being the case, the only option you have for non-polar is the London dispersion forces. Okay, that's it. Non-polar compounds, automatically London dispersion forces. So those are the two forces that we have to deal with. Now, in the level of strength, this was the strongest force, hydrogen bridging force, and the LDF is the weakest of the three. So we're comparing a strong IMF and a weak IMF. Okay. Keep in mind now, once you defined it as the strongest, what does that tell you? That means, and you might just draw it out and picture it, draw spheres to, maybe circles to represent these ammonia molecules. The interaction between molecules there is very strong. Much stronger than the interactions of fluorine, because these interactions between the molecules of fluorine are weaker compared to the IMF. So that tells me right away, strong IMF, it's going to affect my boiling point, my vapor pressure, and my surface tension. Okay, well, let's break it down. Let me clear this up. All right, so here's the formulas. And we determine hydrogen bridging for ammonia and London force for fluorine because it's nonpolar. All right, first question. They're asking you, which one has a stronger IMF? Well, we just went through that scenario. Obviously, the hydrogen bridging force is stronger, which is ammonia's force. Okay. And which has the lower boiling point? Okay. Which one do you guys think will have the lower boiling point? Ammonia or fluorine?
Fluorine.
Exactly. Why would fluorine have it?
It has less. Well, the bonds are weaker, so it can start boiling faster.
Okay, but not the bonds.
Well, the force is weaker, holding them together.
Exactly, because the London force is weaker than hydrogen bridging. Therefore, it would have the lower boiling point. Okay, and is there vapor pressure? Okay, we know we just talked about which is polar. Obviously, the ammonia is polar. Okay, and who would have the higher vapor pressure?
The fluorine again.
Fluorine again, for the same reasoning that it has the weaker of the interactions, the IMF interactions, the London force is the weaker. And then, which if, we're both in the liquid phase, who would have is the least viscous? Who would flow more readily? What do you guys think? Remember, viscosity is a measure to resist flow. And if the molecules are held strongly, they're going to resist flow much more than those molecules that are not held as strong. So what do you guys think? Ammonia or fluorine?
Fluorine.
Fluorine. Okay. Exactly. So it would be the one with the least viscosity. All right, and the more surface tension, again, the one with the stronger IMF interaction, which would be ammonia, would have the higher surface tension. Okay. This here kind of puts it together for you with respect to IMF. As we increase the IMF, viscosity goes up, okay? And the boiling point goes up, and the surface tension goes up. Okay, we get stronger IMF up to the hydrogen bridging. They hold on to their molecules much tighter than London dispersion forces. Therefore, their viscosity goes up, the boiling temperature, boiling point goes up, and surface tension goes up. Because they're holding on to the molecules tighter in the liquid phase, guess what? There's less of them going into the gas phase and resulting in vapor pressure decreasing. Okay. All right. Well, any questions about that? This kind of summarizes these forces that helps you. And when you do compare and contrast between molecules, first determine the polarity. Once you determine what their polarity is, then determine what force they are assigned to. Then by the strength of the forces you're comparing to, then you can determine who's got the higher viscosity or the lower, because this question here could be, as IMF decreases, viscosity, what? It's the opposite of increase, right? Decreases, exactly. So be careful with the wording, read the question carefully. All right. Water, just a quick note about water. We did talk about it, but water is very special. First of all, it has two bonding pairs. Remember, we did the Lewis dot structure, and it has two non-bonding pairs. It's extremely, extremely polar. It's the most polar solvent that we have, and will dissolve literally every ionic compound. But there's degrees of solubility. Obviously, we learned about that. Either you're 100% soluble or insoluble, but even at insoluble classification, there are a few ions still in solution. Okay? Very strong hydrogen bridging forces between the molecules. A lot of hydrogen. Very polar, extremely high IMF. Results in a lower vapor pressure. Boiling point is 100 degrees, 0 degrees Celsius, and high surface tension. And something unique that I spoke before when we talked about density is that water expands when it freezes. So it's in the liquid phase and it goes into the solid phase. The volume for a given amount actually increases, which results in the density of ice being much less than the density of water. Hence, that's why ice, even though it's water, floats. Simply remember, density is that ratio of mass over volume, and the volume just expanded, and so that ratio becomes less than 1. Some pictures, very ordered state. Here's some crystals, 3-dimensional models of water crystals when they're in the solid phase, creating this hexagonal shape, which is unique in nature. Nature has that hexagonal shape is very common throughout nature. And then an image of a snowflake, something unique about it. I'm told that water snowflakes are all unique. Not one is the same. I can't verify that, but that's what they say. Okay, we're almost done with this chapter here, but let's talk about what we call the heating curve. Anytime we're going to heat something, we end up with a curve like this. Let me describe what's going on here. Oh, by the way, I just got to know my internet connection is acting. Cox has been acting up in the neighborhood, so if we lose connection, given the time, we just continue next time. Earlier today, I dropped my connection maybe 4 or 5 times. So, all right. So we have a heating curve. We have temperature here along the y-axis. So we're heating this up, and we have temperature going along the x-axis. So we're adding heat to it. Well, we start off here, and this would be something in the solid form. Specifically, we'll be talking about water here. Well, we start off in the solid form, and as we give it energy, we heat it up. Guess what? Our temperature goes up. Okay, noted by the thermometer, just measuring the temperature until we hit a plateau. We hit a plateau, and nothing, that temperature stays the same until we reach a point here that the temperature then goes up again until we hit a second plateau. Okay. And that remains constant no matter how much heat we put into it. That temperature, which is over here someplace, it could be any value, remains constant until such time we get another jump. Okay. And so we have a rise, plateau, and then a rise. And that's a typical heating curve for a lot of chemicals. All right. So let me go to the next one. What is happening here is this, and we're going to talk in detail about this, but as we start to heat, we get the first rise. It is all solid material, okay? Until such time we hit that first plateau. When we hit the first plateau, this is where solid now is being converted to liquid. We get a phase change. And all the energy that this sample absorbs, is utilized to break up the interaction between the molecules. Okay. It's breaking that interaction up right here, right there, and right there, you know, three-dimensionally. So that's why the temperature doesn't rise. So as long as I keep heating it up, adding energy into it, I turn the temperature up, more energy, temperature stays constant until such time that all of the solid has been converted to liquid. And then at that point, we get a rise. And so at the second rise, it's all liquid phase. Then we hit a second phase. Okay. At the second phase, very similar to what I just talked about, we have the liquid phase, they're interacting with each other. There's a IMF interaction. So now, as we continue to give heat, the temperature remains constant. Okay, because at this stage, at this plateau, all that liquid now is being converted to gas until we reach a point where all the liquid has been converted and we no longer have any more liquid. And then we get another rise, okay, in temperature. And so on these plateaus, next time you're boiling water, make some spaghetti, okay? Once you got the water boiling, this could be water right here. This is 100 degrees, this is 0 degrees. Once you got the water boiling, if you turn that burner up more, you're not going to get any more higher temperature. It's boiling. It's going to sit there constant at 100 degrees until such time that you have driven all of the water off, and then you're going to get increase in temperature. So once you got it boiling, save your electricity bill if you're using electrical or your gas bill, and don't fire it up because you're not going to gain anything. Okay, and the same is true down here at the bottom. Okay. Where the solid is being converted to liquid, there is no change in temperature. All remains constant because at those plateaus, what is happening is that the chemical compound is absorbing that energy to break up the intermolecular forces of whatever that species is. Sometimes this temperature could be very low, depending on the type of force, or it could be fairly high, like, for example, the boiling point of water, 100 degrees. Okay, so during the phase changes, the temperature always is constant, and all the energy goes up to breaking the IMF. It's not breaking bonds. That's important to remember. There's no bond breaking here. All we're doing is breaking those intermolecular forces of the molecules. All right, so that's just an important point. You're not breaking bonds. Okay. Well, ladies and gentlemen, guess what? Congratulations. You got one chapter left. And that one is going to be fairly short itself. I think it's got like 14, 15 slides. And topic matters are not too complicated. So let me stop my sharing. That's all I got for today.